Hello dear students, in the previous session we were discussing about integration, geometrical interpretations of integration, differentiation and intervals, then bounded above, bounded below, supremum, infimum, everything, right? In this session I will just brief all those things once again, then we will move to the next topic, okay? First I will start with the intervals. We have different types of intervals, right? The first one is closed intervals. In order to define a closed interval, we will consider two real numbers, say A and B. These two are my real numbers, such that it should be in the form of A is less than B, right? Then I can define a set X such that X is in between A and B. Here you must observe for closed interval it is less than or equal to. Okay, we can denote this as closed A comma B. Similarly, we have an open interval. The set will be in the form of X such that A is less than X less than B. You can observe the difference for closed interval as well as open interval. Here it is not equal to, it is just less than. So you can denote this as open A comma B. That means if I choose a real line, so if the interval is 0 comma 1, in the case of open interval, if this is the point 0 and this is the point 1, all the points includes a part of 0 and 1. But in the case of closed interval, if the interval is 0 comma 1, including 0 and 1, it covers all the points. That is the difference between open and closed intervals. Similarly, we have semi-open or semi-closed intervals. The set may be in the form of X such that A is less than X less than or equal to B, or X such that A is less than or equal to X less than B. These two are the sets for semi-open or semi-closed interval. You can denote that as open A, closed B, right? Open A, closed B. This is closed A, open B. You can denote open interval in this form also. Similarly, here you can define this open A, closed B as in this form. Similarly, for closed A, open B, we can write it as A comma B in this form. These two are equal, these two are equal, and these two are equal, denoting the intervals in different forms. That's it. Okay. So this is about intervals. Next we will move to bounded above and bounded below. In order to define bounded above, first I will consider a set, subset S, and this S is a subset of your real numbers. Okay. That means all the elements of S are coming from the real number, set of real numbers. So now I have to say that this S is a bounded above. In order to say S is bounded above, if there exists a real number, and I will denote that real number as some B, and this B not necessarily a member of your S. Okay, this not necessarily a member of S, such that X belongs to S implies X is less than or equal to B. If this condition is true, then you can say that S is bounded above. For example, in the previous session also I have given an example. First I will consider S set S as 1, 2, 3, 4, 5. Okay. This is my set and this is subset of your set of real numbers. Now you can observe here In order to say this S is bounded above, there exists some real number B. Since it is not necessarily a member of S, I may consider B as 10, B as 6, B as 8, anything, okay? But it should satisfy this condition. You can observe here X belongs to S, that means each element of your S acts as X, and for each element this condition should be satisfied. If I consider B is equal to 10, I can say that 1 is less than or equal to 10, 2 is less than or equal to 10, 3 is less than 10, 4 is less than 10, 5 is less than 10, right? So here T is the number 10 is called as an upper bound of S. I may choose 5 also. 5, if you consider 5 also, it is member of S and it satisfies this condition. 1 is less than 5, 2 is less than 5, 3 is less than 5, 4 is less than 5 and 5 is equal to 5. That means 5 is a number which is called as upper bound of the element S. This is how we define bounded above. Similarly, I can define bounded below element as if there exists a real number say B. Again, this is not necessarily a member of S, such that X belongs to S implies X is greater than or equal to B. So if I choose example as 2, 3, 4, 5, there exists a real number say B, and this B may be 1, 2, 0, anything. And I should check this condition for each of the element of my S. So 1 is greater than 1 is less than 2, 1 is less than 3, 1 is less than 4, 1 is less than 5. That means this condition is in reverse order, right? B is greater than or equal to X. B is less than or equal to X. So since to each of the element of S this condition is true, so I can say that B is a number which is called as lower bound of S. So this is how we define upper bound and lower bound. The next one is least upper bound, or we can call it as supremum. Okay, so I can define least upper bound or supremum as if the set of all upper bounds of a set, we are considering set of all upper bounds of a set S of real numbers, and obviously in that set there will be a smallest member, right? Smallest member. I will denote that smallest member as some k. Then this k is said to be least upper bound or supremum. Okay. For example, if you have some set of upper bounds like S1 is equal to 2, 3, 4, 5. If this is my set of upper bounds, in this the least or smallest member is 2 and this 2 is called as least upper bound. Okay. Similarly, for greatest lower bound, or I can call it as infimum, here we define that I will consider the same set. Okay, S1 is equal to 2, 3, 4, 5. But here, in order to define least upper bound, we collected or we constructed a set of all upper bounds. But in the case of greatest lower bound, I will collect all the elements of set of all lower bounds. If this is set of all lower bounds, in this the greatest member is 5, right? This greatest member is called as greatest lower bound, or you can say that as infimum. This is how we define infimum, supremum with respect to bounded above and bounded below elements. Okay. So now let's move to the next topic. The next important topic is Riemann integral. Okay. In order to define a Riemann integral, first I will consider a function f of x, and this f of x is bounded function. So obviously if it is bounded function means we will be having infimum and supremum, right? I will denote that infimum and supremum as capital M and small m. Your small m will be infimum and capital M will be supremum. So first I have considered a function which is a bounded function. Since it is a bounded function, obviously it consists of infimum as well as supremum in the interval, that is closed interval a comma b. Okay, that means this is my function f of x, and this function is a bounded function. Now this is my interval a b, right? So now I can divide this interval as number of sub intervals. Say this a is x0, a is equal to x0, x1, x2, or I can make it as xi minus 1, xi, b is equal to xn. Okay, so here in the y-axis I can denote in this way. This is my infimum m and this is my supremum m. Okay, so in between we have points like mi and capital Mi. I can denote in this way. So now we have subintervals of the interval a comma b. That means we are dividing our intervals into n subintervals. So I can write a partition P1 as a is equal to x0, x1, x2, so on up to xn, and this xn point is equal to b. You can observe here, this is my interval a and b. My function is a bounded function in this interval. So the first point is x0, x1, x2, so on up to xn. The last point is including b, right? Because it is a closed interval. So I can divide my interval in this form, and we will call this as a partition. Now using this, mi and capital Mi be the supremum and infimums. Okay, these two are infimum and supremum of the function f of x in the subintervals xi minus 1 comma xi. Don't get confusion with this infimum and supremum and with this, because these two are infimum and supremum in the interval a comma b, that is in the closed interval a comma b, whereas mi and capital Mi are infimum and supremum of the function f of x and in the interval xi minus 1 comma xi. You can observe here, right? For this Small mi and capital Mi are infimum and supremum of the intervals xi minus 1 comma xi, which is for the function f of x, and just m and capital M are infimum and supremum of the intervals a comma b. So now from this I can say that interval xi minus xi is a subset of closed interval a comma b. That means all my points x naught, x1, x2, so on up to xn, these all points are contained in my closed interval a comma b. So I can write in general closed interval xi minus 1 comma xi is a subset of closed interval a comma b. Then this is nothing but m is less than or equal to mi, this is less than or equal to capital Mi, and this is less than or equal to m. You can observe here in this diagram, you can observe clearly. Okay, so now let us introduce a small change in interval as delta xi. This delta xi is nothing but xi minus 1. So first I will consider this inequality. To this inequality I will multiply delta xi throughout. That means you will be getting m into delta xi less than or equal to mi into delta xi less than or equal to mi into delta xi less than or equal to m into delta xi. Since we have I in the suffix, that means there is a variation, right? I don't have only single point, we have set of points. That means I should vary my I. In order to vary my I have to introduce summation in this inequality. So I can rewrite this inequality as summation I is equal to 1 to n m into delta xi less than or equal to summation I is equal to 1 to n mi delta xi less than or equal to summation I is equal to 1 to n mi delta xi less than or equal to summation I is equal to 1 to n m delta xi. I can write in this form. So here, since there is no I indices for m, I can write this as m into summation I is equal to 1 to n delta xi. Similarly, these two can be retained as it is. The last one, you can take m outside from the summation, so it will be m into summation I is equal to 1 to n delta xi. So now we know what is delta xi. Delta xi is nothing but xi minus 1, right? So now let us find out what is summation I is equal to 1 to n delta xi. So I can write this as summation I is equal to 1 to n xi minus 1. Now give values to your I and expand your summation, so that you will be getting x1 minus x0 plus x2 minus x1 plus so on up to xn minus 1 minus xn minus 2 plus xn minus xn minus 1. So you can observe here these two terms gets cancelled, these two terms gets cancelled. So again x2 will gets cancelled with another term. At last you will be getting xn minus x0. This is the value of summation I is equal to 1 to n delta xi. So according to the partition we have considered, P1 is equal to A is equal to x0, x1, x2, so on up to xn. This is equal to B. From this partition, in the place of xn I can write B, and in the place of x0 I can write A. That means summation I is equal to 1 to n delta xi is equal to B minus A. Call this as equality number 3. This is your inequality number 2. This is your equality number 3. Okay. Now using equation 3 in your inequality 2 can be rewritten as m into b minus a less than or equal to summation I is equal to 1 to n mi delta xi less than or equal to summation I is equal to 1 to n mi delta xi less than or equal to m into b minus a. Here your mi delta xi is called as lower Riemann sum and mi delta xi, this is called as upper Riemann sum. Okay, so that is I can write summation mi delta xi as L of p comma f. This is nothing but lower Riemann sum for the partition p and for the function f. Similarly, summation mi delta xi is equal to u of p comma f. This is upper Riemann sum for the partition p with respect to the function f. Now this is for the partition P1, right? So similarly, if we have one more partition, say P2, so I can write let L of P2 comma F and U of P2 comma F. This is the lower Riemann sum and this is upper Riemann sum with respect to partition P2 and for the function f, right? Similarly, if L of P3 comma f and U of P3 comma f we have, then this is lower Riemann sum with respect to partition 3 and this is upper Riemann sum for the partition P3. We can continue in this way, so on, right? So by considering all the partition, I can write L of P comma f as my overall lower Riemann sum for the partition P with respect to the function can be rewritten as maximum of L of P1 comma f, L of P2 comma f, L of P3 comma f and so on. The complete set, if you consider the overall set, in that if you consider the maximum one, that is nothing but lower Riemann sum for that partition P. Similarly, the upper Riemann sum can be written as it is minimum of U of P1 comma f, U of P2 comma f, U of P3 comma f and so on. Okay, so now your lower and upper Riemann integral can be written in the form as I lower integral of the function f is equal to integral lower limit a to b f of x dx. This is nothing but limit n tends to infinity L of p comma f. This is how we denote for lower Riemann integral. Similarly, for upper Riemann integral, I upper line which is equal to integral over a to b, this is upper limit, we will denote in this way f of x dx, and for this we will take limit n tends to infinity for your upper Riemann integrals or upper Riemann sum. Okay, that is limit n tends to infinity u of p comma f. If these two are equal, then we say that the function f of x is integrable function. That means I can write that as integral over a to b for lower limit f of x dx is equal to integral a to b upper limit f of x dx. If these two are equal, you can rewrite this as integral over a to b f of x dx. Okay, this is nothing but we say if these two are equal, then I can represent that in this way, and here your f of x is Riemann integral function in closed interval a comma b, or you can denote that as f belongs to Riemann integral over closed interval a comma b. So this is how we will consider a Riemann integral, and we will discuss the concepts of lower Riemann sum and upper Riemann sum. One more thing is we can divide our interval into n subintervals in the form of, if the interval is a comma b, in general this a comma b can be divided into number of partition as a comma a plus h by n, comma a plus 2h by n, so on up to a plus nh by n. This is equal to b. This is how we divide our intervals. Okay, so here h is nothing but b minus a. In the next session, using this concept, I will solve some of the problems so that you can understand the concept even more better. Thank you.